I'm Mike Matheson, Managing Director of Cognite.ca, and will be moderating today's session. The series is jointly presented by Cognite.ca and the Canadian Construction Association. The R&D Showcases are part of a broader initiative undertaken by Cognite.ca and the Canadian Construction Association to help the construction industry more fully leverage Canada's academic research enterprise. Another major element of it is the Construction R&D portal, which can be found on the Construction Association's website. Using the R&D portal, you can see recent construction industry relevant research and search for researchers, facilities, and IP that can help your business address your company's next innovation challenge. I posted a link to it in the chat and would encourage you to check it out when you have a few minutes. Our format today will be a 10 to 15 minute presentation followed by a 10 to 15 minute Q&A session. If you have questions for our presenter, please click the Q&A button at the bottom of the Zoom window and enter them into the box. I'll then read them out during the discussion portion of the program. For today's R&D Showcase, I'm pleased to welcome Dr. Dominique Derome. Dr. Derome is the Canada Research Chair at the Université de Sherbrooke. She will be presenting on long-term performance of the building envelope in the context of climate change. And with that, I'll turn it over to Professor Derome.
Thanks, Mike. So thanks for the invitation. I will just share my presentation. Okay, good. So I want to present to you a bit about the outcome building envelope is a system that needs much more information that we may think when we want to understand its behavior and particularly its long-term performance. So the building envelope is a crucial element of the building in terms of maintaining an indoor environment that is comfortable, that is healthy, and in terms of low energy use by the building. Also, what is becoming more clear, it is that also it has an impact on the urban climate, where you could see that the urban climate has a different set of conditions from the inside, but that is affected by the presence of building. And that, so we have to think of the building envelope as a system that is more complex and maybe require a new type of considering. So when I'm talking about today is really I will focus on heat transport and mass transport. So it's the heat, it's the water that we find in the environment, and it's the air. All of that makes the physical aspect of the built environment, the interaction with the built environment, and this is where we will have to look at outside at wind, rain, and sun. And why we do that is that one of the new challenges that came upon recently was those heat waves that can really have a critical damages, and this is an example from the Montreal heat wave of a few years ago, where you had people dying in excess to what people dies usually, and there's 70 people that died there during this heat wave in less than a week. And the way we build the environment is partly responsible for that. So what is maybe not known is that in the heat wave, the people that die, they come in excess to the normal death level. It's not people that would have died anyway in the next year. It's really an excess, because heat load on the body is an additional load that some people cannot cope and leads to disorder and sometimes death. So, for example, in Montreal, you see how you have a sector of the island on the city where you have local heat islands. So you have the global heat island effect of the full city, but additionally to that, you have places within the city locally that are even hotter. And this is one thing that you have to take into account when you look at the building envelope, is that the conditions outside are not necessarily as simple as what we think. So what if we looked at the envelope and looking at really what is happening around in terms of airflow, in terms of rain deposition, in terms of radiation exchanges with the sun and with the sky in between buildings? What is the role of all the porous media inside in making the envelope on the streets? And then, of course, This is all the physics that we have to look into. Physically, it means that we cannot just make a simple representation of all those physics, that we do it with the exact equations and we do the exact wind flow. And if we can do that in a good modeling environment, we can, like what I'm proposing here, we can get a very good understanding of what is happening around the buildings and inside the building. What this means is that you can actually understand what is happening in the building envelope outside in the street and inside the building, if you take into account all the exchanges in the proper way. And this is not the current way now. Now we have the codes that require that we take weather data to apply on the building. So we bypass all the impact of the local urban climate. So how we do it? Well, first we do actual wind simulation of looking at how is the flow. We can in that put rain, so we can look at exact rain deposition of all the droplets. And here you have a representation, like it's actually a calculation that shows how all the different droplets find a place in the built environment, and how some facades are more wetted than other ones that are protected from the rain in certain rain event. So this capacity to model rain deposition on buildings can allow, for example, to understand in a balcony that you have different conditions of wetting in the different levels of the balcony, can have different conditions of solar radiation, so that people living on the top floor, on the bottom floor, don't have the same local climate when they come outside in their balcony. You can also look at this rain deposition in terms of a source of moisture that can cause damage. And for example, this is a historical building where we looked at how much the rain was deposited and understood why there was some places of the masonry that was going to further degradation. So when you talk about rain, you have to look at droplets. And so here I'm just giving you a flavor of what it means to look at different droplets, and understanding that within the built environment, droplets have a big array of different behaviors. They can deposit, but they can splash. And then if you have different roughness, different porous material, you can look at, for example, here, how droplets on the stone can actually penetrate the masonry and distribute. So here you can look at how the water is deposited and then absorbed in a porous material. This is neutron radiography. And after that, we can quantify not only the quantity, but the rate of distribution of the moisture. And we can use that to look at modeling. So here, another example where we look at water to look and compare with modeling is a sample of masonry where you have brick, mortar, brick, and then we put that in contact with water. And we look at the propagation of the water. That's a liquid uptake experiment where you have the water coming into the masonry. And the purpose here was to understand what is the role of a porous material interface with another porous material. So brick has a pore system more open, bigger pores. The mortar has a very fine system of pores. So from big pores to small pores, it's easy for the water to come in, but from the small pore to the brick, you have what you call a capillary break. And here, this is what we could put in terms of actual quantification, looking at those measurements and then simulating that. So here you have a comparison dash line, full line of measurements and simulation for the masonry. Another example, another material that we use a lot is wood. And if you look at wood during absorption of wood, you can see how it not only take up the water, but the water leads to a big deformation. And this is very important to look at all the physics that lead to understanding what is happening in different materials that we have to take into account. And the swelling of wood due to sorption, desorption. Here you have the sorption-desorption result with the swelling at the cellular scale, has also to be taken into account. So why I talked about a lot of different scales, from urban scale to material scale. And I'm coming back now just to look at what is the impact of another material, which is now leaving the tree. If we put that in the urban scale, and we can look here at what is the impact on the trees to have some trees, and looking in terms of shading, in terms of temperature, and in terms of wind, looking all of that together, you can see the temperature difference due to the presence of trees in the cities. So these, then you can look at surface temperatures, because here you have all at the same time, and the sun and the wind, and the fact that the tree is a source of vapor because of photosynthesis. And you can look after what is the impact on the street for people to be in the street in terms of comfort. You can also look what is the impact of vegetation or the mean of refreshment for the building in terms of cooling load. That I'm not presenting that. You can also, with the work frame that I'm presenting here, we can look also at what is the impact of climate change. So just one example at using a urban configuration. This is in Zurich, where I was working before coming back to Canada, where we can look at the square and put some vegetation here, a piece of grass in the square, and look at how much cooling is we can get in terms of temperature due to the presence of grass compared to a square which was just minerally used. So here you maybe you recognize the Parliament of Canada. So this is a study where we look at rain deposition on the Parliament also as a source of degradation, and see if what we should take into account when we look at the conditions of the loading conditions on the masonry building, and also extend that with what will happen in the future in terms of climate change and the changes in load deposition, rain load deposition. So I showed you some examples for different type of modeling, different type of imaging, different scales of doing all of that. Thank all my co-workers that worked to me in the past, and I'm thanking you for your attention in this really, really brief presentation and opening on maybe for you other ways to look at material, porous material, to look at wind flows, air flows, climate modeling in the urban environment, to look as all of this as input for building energy simulation, to look at the impact of climate change and more. I'm finishing just with here with the simulation of how water gets into wood. So this is actually a molecule by molecule simulation of water getting into the wood polymer, and then leading to swelling of wood. So this is another scale of modeling, just to finish as a nice image. So I thank you, and I guess I will stop to share now.
Thank you, Dominique. We'll now begin the Q&A session. Just a reminder that if you have a question for our presenter, please use the Q&A box at the bottom of the Zoom window. I'll try to get through as many of your questions as possible during the time remaining. So, Professor, you covered a bunch of different ways that we can do modeling in terms of on the built environment from a variety of different scales. When you bring all of these techniques together, to you, what are the most important opportunities or impacts that these techniques can have?
Well, the one aspect that is absolutely not done now is when we design building is to consider the local climate. So we use weather data like that is measured in the airport. The temperatures, the conditions at the airport that we use as in boundary conditions when we consider buildings is very different to what is happening in the urban climate. So we talk about a big over design of heating and cooling equipment. In some cases, over design or under design, depending on the cases, compared to if we could just use the exact conditions. The other big, in addition to the fact that in cities it's warmer and what we call the heat island effect of cities, there is the fact that the heat waves have even more impact when it comes on cities, and then the the heat wave change, like the temperature are so much more extreme compared to what we use in base data. So that if we want to have buildings that can go through a heat wave and have people comfortable, the input, the boundary conditions are very different from what we are using now.
And so based on where the research is today and where you anticipate it's going, both your own work and that of your colleagues, where do you think we'll be in terms of being able to model out some of these impacts, and how can you imagine that would be used in application by folks in building management or the construction industry?
But it is already planned that the next building codes, national building codes, will require designers to design in terms of current and future climate. So we will have to design in terms of taking into account climate change. The way it will be done is still just with tables, like database. The fact what I can provide is that these weather files are more and more accurate, and they will always, it's for a designer, it's the same weather files, so it will be always the same level of it's easy. But what we can have is that they can have an idea of how resilient is their design compared to future climate change.
When you look at all of the various levels that you presented the modeling on, there's a lot of variables. There's clearly a lot of modeling, a lot of simulations that were run to do that. For a building, for a new building going up, what sort of cost scale is it to take this more dynamic, comprehensive approach to modeling versus, I think you described it as a bit of the database approach? Is it a big sort of order of magnitude difference, a little bit more expensive? Can you just, how would we think about that cost?
Well, it will depend if you want to design something that is new or something that is more regular. So for solutions that are standard, there's no need to go to the modeling. You can just use the inputs, the boundary conditions as input, and look if your system works. But sometimes if you go for systems that are more passive, that have that rely on natural ventilation, there you need to go into more advanced type of modeling. So even without considering all the aspects that I'm showing, there is a need, or there should be a need more and more for some conditions, for some integration of renewables, or for some systems that are more passive, to use simulation like CFD, so that you need to look into account of all the airflows to make sure your system works, and that this requires a fair amount of investment to make sure that you can get a simulation that is helpful for design. So it is also a skill that is not so much shared yet by designers, but for sure at Sherbrooke, with our future building engineers that we are teaching them CFD so that they can be prepared to do that when they get on the market, because it is a skill that will be more demanded.
So there's a specific question from the audience about one of the slides that showed the impact of vegetation when included into a built environment, and there were two spikes that were separated by a low dip between them. Can you explain what was happening with those?
So here, the point of observation was under the tree. So if you have the tree here, the sun was on that side. So when you were on the sun was moving all throughout the day. So when the sun was here, it could lit under the tree, and it started to heat locally. So even though you were under the tree, you still received sun. At one point, the sun was above the tree, so then you were in the shade, and it went very more comfortable. Then when the sun went the other way, it lit again. So the capacity of the tree to be a very good shading device and presenting good conditions for comfort, that we know. I don't need a model to tell you that you feel good under the tree, but I can calculate it. And then you can see that it's not all throughout the day.
Perfect. And so I wanted to pick back up on something you said a moment ago about the graduates that you're training at Sherbrooke and the skill sets required to do a lot of this modeling and this work. Can you talk a little bit about how a business might think about the skills and capabilities they would need as they think about integrating this kind of more sophisticated modeling into their own project planning processes and
Well,
design work?
if you talk about engineers that look more at the HVAC system, for sure you need to have people that can do CFD modeling to really understand the airflows in the system, and then integrate to this aspects like solar radiation or exchanges with neighbors of radiation, and also there is a capacity there to take to account novel type of features that are complementary to HVAC. There is also, if you want to understand the building envelope and the long-term behavior of the envelope, you need to understand, you need to go towards modeling of the envelope that are much more advanced, and then understand what are the physics in porous material of the transport of heat that can take into account not only the transport, but also look at if the water present there can lead to damage. So this is also hydrothermal modeling of the building envelope is a skill that becomes more and more needed and can also be part of a mechanical engineer team or of a building scientist team in different and there's also another aspect is where those for example, if you go towards wood and you want to consider not only moisture content in wood but also the deformation of wood. So even if you're a wood structure, so if you do structure design of wood, you can also use mass transport to understand what happens to your wood structure.
So for a business that might not be doing much in terms of modeling or this more dynamic form of modeling, jumping all the way to some of the more sophisticated techniques you presented earlier might seem daunting. Is there a good starting point, entry point that they may want to think about exploring where they can start to leverage some of the possibilities that you laid out without it being as seeming as difficult as going all the way to the very technical, very specific pieces that you laid out?
Well, of course it is. It's a steep learning curve, and there are some of the tools there require some background knowledge that needs a fair investment to get very adequate with. I think though that in terms of building envelope modeling, there are commercial tools like that are available that can provide a good environment to make sure that you get good results and that you don't need so much. So what I do is not commercial tool based, but there are commercial tools that can be quite good and give boundaries so that you cannot go something totally crazy for building envelope design. In terms of CFD, this is not something that has I would not say yet the capacity to, I don't see yet the tool that you can use without the knowledge base and that can give you a good feedback if you're going to do something wrong. So CFD, you still need a bit more knowledge. And so the best way then is just to, if you need to go with special firms that can provide consulting on those specialist aspects.
And can you talk a little bit about, and this one's from the audience, the difference in heat distribution patterns between flat roofs or versus sloped roofs, or I guess other possible configurations?
So the impact on the temperature of what?
Yeah, and heat distribution and the patterns associated with it.
Okay, so if it's heat distribution, where so if it's in at the street level, so if you're if the buildings are 3/4 floor high, the shape of the roof there will not have a big impact what happens at street level. I don't know if it's the question, but it will have a big impact on the mixture. So so if you want the city to cool down, you need the winds to be able to remove some heat from in the streets. So if you have the roughness of all the what you have on the roofs makes that you have enough turbulence to remove what is in the streets. And that is not really because of the shape, flat or slope that we see. It's more because the roofs are full of stuff, of all the HVAC units and all that. So you have enough roughness there to get a good turbulence, to get a good mixing of the air, and get the wind to be turbulent enough to go into the city, into the streets, and provide some cooling or refreshing of the streets. I don't know if that was the question.
I think it was, and if not, perhaps the asker can ask a clarifying question. We've only got a couple minutes left, and just wanted to maybe think a little bit. When we think about the building envelope and a number of the techniques you identified in terms of the modeling, a lot of those provide longer term solutions as you think about the entirety of the built environment. Can you talk a little bit about what some of the shorter term opportunities might be for improving building efficiency, comfort, health in these sort of extreme heat waves?
So one thing short term that we are looking really a lot is if you know there's a heat wave next day, what to do.
Right.
And then so we did different simulations to look at if you come with the truck in the morning and you wet the street, how much water you need to put there and what type of asphalt you need there, so that the impact is felt throughout the day until the next morning when the truck can come. And we really could optimize the amount of water you put there and calculate the effect that because of water evaporating, it takes heat because of the latent heat. It takes heat away from the asphalt and it prevents the solar radiation to be absorbed by the porous asphalt, by the asphalt, which is has a capacity to heat up very much. So you totally change the conditions of the street looking by decreasing the temperature, and you can actually decrease the air temperature up to 2 degrees. It doesn't sound like much, but the air temperature for the street, 3-story high, by 2 degrees, it means that you could do a fairly good cooling. And then it means that in the buildings, if you have natural ventilation, you see the impact. And also if you do cooling and then your intake air temperature is as 2 degrees less, also you can see the impact in terms of cooling. We are looking also at the impact, trying to understand the impact of vegetation to this extent, and also to see if we can retain the water on the surface using different type of porous system on the streets.
Well, that's great. And that pretty much brings us to time. So first of all, I'd like to thank Professor Jerome for their presentation. I know I found it extremely interesting, and I'm sure others did as well. I'd also like to thank Mary, Kenny, Nicole, and Derek, and the rest of the team at the CCA who have been so instrumental in pulling this session and the whole series together. Without them, this really would not be possible. Lastly, I'd like to thank all of you for coming out today. We know your time is scarce and precious, and we really appreciate you fitting this into your busy schedule. On that note, we're really focused on ensuring these sessions are as valuable for you as possible. To that end, we've created a short evaluation form, and we'd really appreciate it if you could fill it out. I've pasted a link to it in the chat window. In addition, it should open in your browser if you haven't already closed the Zoom tab. It should take you about 1 minute to complete, and your honest feedback is critical to us. Thanks again, and I hope everyone has a wonderful rest of the day and week.
Thank you.